So first, I would like to thank you very much for inviting me and for having the patience to wait for my technical problems. I had to switch computer 2 times because some crashes, but now finally it's working, hopefully. I will be talking about scroll wave dynamics in confined geometry. Actually, these are 2 parts which I will be talking about. And I have seen that in the previous talk, the Belousov-Zhabotinsky reaction has been shortly introduced, and they had a nice movie and a picture of that. Well, this is an excitable system which can show waves and, well, at the conditions also oscillations, and can be modeled relatively easily, having diffusion terms and reaction terms. And you can use different kind of models as you wish. The oreganator, which is chemically a little bit closer, and the Barclay model as a generic model of that. And we will be using this Belousov-Zhabotinsky reaction because we can not only run experiments in 2, but also in 3 dimensions, which comes very much closer to that what we have in the cardiac dynamics. So in this sense, it is an experimental system which is excitable and has the same kind of properties, or at least some of the properties that a cardiac system would have, which nowadays relies heavily on computation and simulations, and experiments are really improving to get those 3-dimensional structures visible there as well. What we have to be looking at is we have rotating spirals. They can either rotate rigidly or do some meandering. Same story also goes for the 3-dimensional counterparts, scroll rings, which may be straight, scroll waves, which may be straight, scroll rings if the filament is closed, and they can be even twisted in this kind of issues, which we'll be seeing here. I will be addressing in this talk only single scroll waves and looking at their dynamics. Well, the motivation for doing so obviously is you have a system which has nice physics, which is very much similar to that what you know from cardiac systems. And this, well, I guess the most of you don't are already very tired to see this kind of nice movies which we have here. So this the normal heartbeat can change by some disease to tachycardia or fibrillation, tachycardia being 1 spiral over the ventricle in this case, and spiral dynamics and spiral chaos, spiral turbulence in the case of fibrillation. And let's see what we can do with our experimental system, looking at scroll waves. Well, so far, most of these experiments have been done when the scroll wave was oriented in parallel to some gradients, if this is the gradient. In our case, we've been looking at something, what happens if they are perpendicular to a gradient, and from the second point, what happens if you really run them in a confined geometry. That's what I really promised you. What we are doing in the experiment is we have some optical tomography, where we have here a small reactor which is rotating at a certain speed. We have here a blue LED light, and we just take all these images at intervals of 1.8 degrees, and we take 100 pictures to have 100 projections. And from these projections, by applying the radon transform or the inverse radon transform, we reconstruct this 3-dimensional object. That's the idea. And the Belousov-Zhabotinsky reaction, being colorful, as we have seen in the previous talk, red and blue, is quite nice that we can really look at them and reconstruct this from the red light. The way of starting this kind of 3-dimensional scrolls is that we have here first a reactor where we have the BZ reaction, which is just excitable. We insert a partition screen and then an L-shaped wire, which we just put there. So there's an L-shaped silver wire, and the silver wire starts the reaction. And once this wave starts propagating in a certain distance, then we have this wave propagating, as we see here. And then we remove this partition sheet, and the gel is still a little bit soft. It will cure, and then we have here 2 open edges which will start forming scroll waves, and we'll have two filaments. We wait until one of the filaments hits the bottom, so we are left with one filament which we are looking at in the experiment. So then we close the whole thing and we start the things. Okay, what we are going to do now is to look. Where did we start this here? No, this is the wrong thing. So right, what we are going to look at in the first point is we are going to look at the response of a scroll wave, which is in one of those cylinders. However, the filament, which you can see here, this is this curve, is perpendicular to the z-axis, which is the long axis of the cylinder, and x and y are the axes where we have the, well, which are perpendicular to the cylinder axis. And what you see here in this experiment is that we can have three kinds of answers. Well, if we run this whole things in a condition where the filament is really well attached to the wall at the 90-degree angle, we will have filaments which will remain unaffected for the duration of the experiments. However, we can have a different issue, that we can have a filament which twists in from one side. So here in the right side is the filament, gets twisted and they get straight around, which is a situation which you can also see if we were applying a gradient from right to left. And we have a filament in this part number 3 as well, where we have a filament which will start twisting in at one end and twisting in at the opposite end as well. So we can have twists from two sides, which is quite an awkward situation. Well, if the filament, first part, if the filament remains unaffected, can be seen here. This is this picture. We'll see this, the reconstructed filament which we have here is this line from 0 to 20, that's the, or 21, that's actually 21 millimeters, that's the diameter of, sorry, of our cylinder. And it will be fine and unaffected as long as the filament attaches to the wall is at a 90-degree angle. So it's really fixed quite well. Then the filament will, well, maybe shorten until it gets the smallest density, the smallest length, and that thing is fine. And here's the filament which I've reconstructed, and this is quite okay. The other thing is, if we have if on the one side the filament is really perpendicular to that, is a 90-degree angle, and very close to the other angle, this angle is not 90-degree anymore. Locally it is, but at a small distance. What we will have is a tilted filament, and this filament here, which is not attaching in a 90-degree angle, this will feel that there's a gradient in this whole issue, and then we will figure out that in the beginning of the filament will shorten, as you can see here, from 61 to 120, 190 minutes. However, it will start developing one twist on one end, because depending on the height, you have always oxygen penetrating, and oxygen is a gradient of, creates a gradient of excitability, so it can create scroll waves which are twisted at one end. And this is something which you can look at. What's the phase of this filament starting at 0 here at the one end, and how much is it twisted? So we have a twist in our experiments of around 300 degrees. And if you just say, okay, well, this is the filament, you arbitrarily set one angle at 0, and then you see the difference, and then you see this twist arising. Things can be simulated as well. Here you have a simulation using the originator model made by Sergio Alonso. And what you see is that in time the filament shortens, and at the end where, no, there's no shortness, the filament gets a different position, it's higher than lower, it's closer to the air. So at this part we have a relatively constant phase, but the phase, there's a phase slip as the filament starts to get twisted. Similar situation can be found that we have a filament which we have both sides. Is the one side we have here clockwise rotating filament, and the other one, the other is a counterclockwise rotating filament. If you just see the two sides, if this filament is U-shaped and both ends, it's not really at a straight 90 degrees angle hitting the borders, which will be here. Then we see that this filament in the beginning has a certain shape, and then you see that it starts getting some twists from both sides. And here you have a nodal plane, which is quite straight. And if we reconstruct this whole filament, yeah, then what we see is that we have the face and the slice, and the position on the filament tend to be around the middle. And depending on these different times, we will have a filament which is twisted to one side, clockwise, counterclockwise, and there's a nodal plane where there's no twist. And this is something like, I'm not working, like this starts rotating at different sides, and what we get is at the very end, something where there's no phase shift in the center, or at least very low, but phase shift at both sides. And if you just see that with time, this nodal plane, the length of the nodal plane gets shorter and shorter, but persists and will remain like that. This is something which you can get. So it's possible to get filaments with two twists which have opposite handiness, which are connected by a nodal plane which has a minimal length, which can be, which is related to the negative line tension which we have. Yeah? And depending the way this filament is done in respect to gradient, we have well, it's the same situation, but we have either a shift, a decrease, or an increase of the phase at the nodal plane. So this kind of exists in slightly U-shaped filaments. They can be calculated like that. Here you see the filament will be here. You see that they have two twists of a different handedness. And here again is the position around the z-axis, and here the phase shift at here at the nodal plane, which in the simulation becomes very close to a point. And we can look here at the twists which we have in experiments and simulation, and calculate well, what's the twist per time. The second part, and that's the title of the talk, what happens in a confined geometry. So far, this was a cylinder where we have run our Belousov-Zhabotinsky reaction, our scroll wave in a three-dimensional object. However, a heart isn't really a three-dimensional bulky object, but is a hollow muscle, which has some kind of relatively narrow tissue, relatively narrow. It's not, the left ventricle is not really that. So we have decided, okay, well, let's have an experimental realization. That would be the following. Here we have gel. It's a cylinder, which is a cylinder jacket, and there's an internal cylinder which just contains, so to speak, some other gel where there's no reaction going on. And so this would be at this intersection S2 is just a ring with gel. This gray area is where the reaction goes on, and we can start this whole situation, the whole experiment. And we always have starting conditions where we have a straight scroll wave, which is started parallel to the z-axis. So it means we started here, let's say, in one side. And here we see the scroll wave rotating. Here is the filament. And here is the other waves which are there. And here is this internal circle, which is this empty area where the reaction cannot get into. So it starts emanating waves, which then get at the other side. Well, they join together and form a wave propagating to the other end. And what we see is that we have three typical cases in our experiment, which we need to consider, or have to consider. The first one, which is the boring one, so to say, is the filament remains straight. So this is exactly what here is. What's the situation here? So if the filament, if you started in a little bit, well, thicker cylinder jacket, so it means if there is sufficient width of this annulus, then the filament has no reason or no noise, no motivation to touch the lateral wall due to any noise. It will stay like it is. It is kind of dynamics that the filament remains straight throughout the experiment. Well, it's more probable or it's preferred as the thickness of our cylinder jacket increases. However, what we don't see is, in any case, on other experiments, even varying our central gap, is we always saw that these two waves which will come, they will join and form a wave which will then a joint wave, which then will propagate away. We never see the formation of an additional filament, which will be there, like we would expect, let's say, for an re-entry in our case. So we don't see that. We also observe filament reorientation. And this is one thing what you see here. Here you see the front picture. Here you see the scroll wave, which originally was started along the z-axis. At the end, it has shifted or has turned its axis by 90 degrees. Here's the frontal view. Here's the lateral view of this whole thing. Here is this cylinder which we are looking at. What happens is this kind of dynamics happens if, by some reason, by some noise, the filament hits the wall. And two opposite walls of the cylinder jacket, this would be the outer wall of the cylinder jacket, that's the gap of the cylinder. If it hits this wall, these two walls, then what will happen is what we have seen already, because the gradient, we will have a reorientation and a shortening of the filament. Yeah? And this gets more and more probable as the gap or the cylinder, this gel here, as this gets narrower, because then some noise will cause the filament to drift a little bit, and the probability of hitting the two walls is there. And here we have this angle theta, which is the inclination angle, which we'll be measuring. And we have measured the dynamics of this kind of reorientation. And here's the length of the filament until the point zero is, the point the point in time where the filament hits both opposite walls. And then we just look what happens. And we can fit this linearly with an exponential function and determine the constants around that. And this angle, which is, we also have measured this angle and can fit it simply by a geometrical argument, and it fits it reasonably well, given the accuracy of the reconstruction of the filament in the experimental data. Again, what happens here as well is, as you see here, the filament here, it will just last from here, from the cylinder to from the inner to the outer edge of the cylinder. At the opposite side, we still see that we have an extended wave which has been formed from the fusion of these two waves that came around the filament. We do not see any production or event or adventure of any new filament and a new scroll wave at the opposite end, where the two waves which meet each other join. Yeah? And the third case is something which is, well, also boring. What can happen, obviously, and this is already here seen here, what these two parts of this filament which remain, they are stuck or bound to the same or to adjacent walls. Yeah? So then what will happen is, then the filament will vanish if they are attached to the same or the adjacent walls, because what we will have is we have a negative line tension, filament will shorten, and what we see is that this the graph, it will be shortening until it gets here, and here we see this kind of experiments, and the filament will either disappear or collapse to a point source. This depends on the gel. If we were lucky, or when we're lucky producing gels which were extremely clean and homogeneous, then they disappear, and if there is some kind of little bit of impurity in the gel or some little bit of grains, which then we will get we'll anchor it to a point source, and again we can determine this constant. It's not that nicely done, because if we just to reconstruct, because we have only the outer wall and there the error is a little bit bigger, but nevertheless we can fit it by the exponential laws, and we get more or less the same kind of data, saying this is something which can happen. Okay, just to sum up, that's what I wanted to convey to you, is that we have an important issue here, is that we can reorient our filament, and this is a this has some implications that if, let's say, the tissue is really very narrow, or the reactor is really very narrow, we can have a reorientation of the filament. This means, in terms of cardiac dynamics, we could expect, or we should be aware of, that some filament which would be intramural, so which is perpendicular to the two walls of the heart tissue, can, by some accidents, if this tissue is small, reorient to be a transmural. Often this happens, to have a transmural situation. This happens, and however, we don't, it's very rare, or actually we have seen only once, that this kind of transmural orientation would give way to an intramural orientation. So it's backwards, simply because here we have a very short filament, and this filament remains short. So as thinner these walls are, or these tissues are, this reorientation gets more and more probable. We have also changed the gap width here in the center. We have never seen any advent of new filaments at the other side. However, I could imagine if this gap width gets well, narrow enough, then this could happen. But this never observed in our experiments, since we never had such small inner cylinders, which less than 3 millimeters of outer diameter. Okay, and with that, I would like to just conclude. So we have seen that gradients and can affect even a scroll wave, whose filament is oriented almost perpendicular to the gradient. Well, if it's really perpendicular to the gradient, then there's no effect. We have seen that. However, if there's some deviations, small deviations at the very end, if they don't really hit the walls, the boundaries in a 90-degree angle, so such small things, then we can have either a one-sided twist of the filament, closer to the higher value of the gradient, or if you have some kind of U-shaped or a slightly U-shaped filaments, then we can have twists of opposite handiness, and what the twist will increase and create a nodal plane until the nodal plane gets to a minimal distance in the experiments. We have never seen a breakup of this kind of filaments with opposite twists. And here's the other part, the effect of confined geometry in a cylinder jacket. Well, the three things which we can look at, so the scroll waves, they can remain unaffected, well, stay vertically, if the cylinder jacket is sufficiently wide. Well, this can be relatively narrow, but the wider it is, the more probable it is that there's filaments remain unaffected. Interesting parts, if both lateral walls are hit by the cylinder jacket, we have a reorientation, which are really relatively simple kinetics, and they will orient from parallel to the z-axis to perpendicular to that, shortening the filament lengths. And this is favored, and the narrower this gap is, because they need to have the filament hitting these two sides at the same time. And if the filament hits the same wall or adjacent walls, then obviously this filament will also decrease in size, and it will vanish either altogether or to a point source. And in none of these cases, at least in the Belousov-Zhabotinsky reactions, we have seen information of any new scroll waves at the opposite side or any other side of our experimental setting. With that, I would like to thank my students, Christian Bruns and Ines Kupis and Patricia Demlo, for these experiments, and Marcus Baer and Sergio Alonso for helping in simulations and with very intense discussions. And with that, I would like to thank you for your attention. And well, this could be the next challenge, but Berlin is not flying anymore as well. Thank you very much.